this question, a message signal having a peak-to-peak value of 2 volt and a root mean square value of 0.1 volt with bandwidth 5 kHz is sampled and fed to a pulse width modulation system that uses uniform quantizer. The PCM output is transmitted over a channel that can support a maximum transmission rate of 50 kbps. Assuming that the quantization error is uniformly distributed, we have been asked to find the maximum signal to quantization noise ratio that can be obtained by the PCM system rounded up to 2 places of decimal. A detailed explanation on the concepts involved for solving this question can be found from the NPTEL course Principles of Digital Communication, Lecture 27 by Dr. Shabbir Merchant of IIT Bombay. Now we will look at some of the concepts involved. The first one is the channel capacity. Channel capacity is the maximum rate at which information can be transmitted over a channel error-free. By error-free, we mean that we can still design an error control code with a very low probability of error such that it can be considered negligible. Hence, C must be greater than equals to RB, where RB is the bit rate. For PCM system, RB equals to NFS, where N is the number of bits we want to transmit and Fs is the sampling frequency. Next we come to step size for PCM. Delta is the step size is given as V peak to peak by total number of levels. Here total for n bits, total number of levels is 2 to the power n. Then the noise power for uniform quantization is given as NQ equals to delta square by 12. We know that noise lies from minus delta by 2 to plus delta by 2. Since it is uniform quantization, the amplitude is 1 by delta. On solving for the variance of such a distribution, we find that the variance comes out to be as delta square by 12 and the mean is also 0. Hence, the noise power comes out to be as delta square by 12. Now, when we design a transmitter or a receiver, what we don't have in control is the channel and hence the channel capacity. What we want is to have as low noise power or quantization noise as possible. In order to have the least quantization noise, the step size must be reduced. In order to reduce the step size, we need to increase the number of bits, and if we increase the number of bits too much, the bitrate might go over the channel capacity. So that is a constraint that we are facing. So in order to solve this, we find the maximum value of bit that can be transmitted n, and for that maximum number of bits we find the suitable step size, and for that step size we get the minimum possible quantization noise power NQ. Next we will look at the solution. So here we have been given FM as 5 kHz. So Fs as equals to 2 FM equals to 2 into 5, 10 kHz, and channel capacity given is 50 kbps. Now we have seen that C must be greater than NFS and we have to find Nmax such that Nmax equals to C by Fs. So we have 50 by 10 equals to 5. So the maximum number of bits that can be transmitted through this channel must be 5 for error-free transmission. So using Nmax we find delta min, that is equals to V peak to peak by 2 to the power n max. So that must be 2 by 2 to the power 5, and that comes out to be as 1 by 16. Now the minimum quantization noise power comes out to be as delta mean square by 12, and that is 1 by 16 whole square by 12. So that is 3.25 into 10 to the power minus 4. We have been asked to find the maximum signal to noise quantization ratio. So SQNR max must be equals to signal power by NQ minimum. What is signal power? Signal power can be found out from the RMS voltage given, and it is 0.1 whole square equals to 0.01, and NQ min has already we have found that it is 3.25 into 10 to the power minus 4. So SQNR maximum comes out to be as 0.01 by 3.25 into 10 to the power minus 4, so which comes out to be as 30.769. But we have been asked to find the answer rounded off to 2 places of decimal, so it is 30.76.